All right, so I want to pick up here because I know this is where we left off on Thursday, and we'll talk about the videos that y'all watched on Friday in just a second. So remember, this is the BBC method, okay? The balance, bust, and cancel. I'm not going to write the entire. Did we do the first one? Did we do both of them? Okay, good. I didn't remember exactly how far we got on this, so we did both of these. All right, fantastic. I didn't, for some reason, I didn't think we did the last one. All right, great. So we've seen that. We've seen this. So really, this is where we are. So I'm actually going to give you guys a chance. I'm going to pause the video, and I'm going to let you work this out. So let me explain this. I'm going to do just a few of the examples for you, and this will make a little bit more sense. So here's what we need to do with this. We're going to pretend that the top row of solutions. Now, when I say solutions, what state would that be? Aqueous. And what's in an aqueous solution? Ions. Okay, and water. So all of those are ions, and we're going to pour them into all the vertical solutions. Okay, so what we're going to try to do is we're going to take beaker A and beaker B, and we're going to pour them together and see if a solid will precipitate out. So let's look at all of the top row solutions. Based on the solubility rules, the quiz you just took, how do you know that none of those would be solids? They all have nitrates. Okay, so all nitrates are soluble. Okay, let's look at the vertical column. How would you know that none of those would form precipitates? They all have a group 1. Okay, so potassium and sodium, they're all group 1s, right? So all those are soluble. So here's what we're trying to figure out, is if we take the top solutions and mix them with the vertical solutions, would a precipitate potentially form based on your solubility rules? So I'm going to do one or two of these, and I'm going to give you a chance to go through and see if they will. So what you're really going to have to do is you're going to have to mentally do double replacement reactions. And so this is going to give you an idea of how to, let's see how quickly you can mentally kind of figure it out. So let's look at the top left box. So when I mix NaNO3 and KCl, who is Na going to be with on the product side? Cl. Would that be a solid? Why? It's group 1. Okay, very good. So we know that's not going to happen. All right, what about potassium, or who would nitrate be within the next one? Potassium. Would that be one? No. So would a solid precipitate form in this reaction? Nope. So let's put an X in that box. So no solids. All of these are aqueous. We're going to see if when we mix them, if we get a solid precipitate. So let's go to, we're going to go right. Okay, so who would lead be with in the double replacement reaction? Would that form a precipitate? Yes, very good. So we're going to put PbCl what? 2. Fantastic, because it's lead 2. All right, who would nitrate be with in that reaction? Potassium. Would that be a solid? Nope. So we're gonna leave it on. So that's the only one we're gonna get. Does that kind of make sense what we're doing? All right, let's do one more. I'm going to go back to the first column and go down one. All right, who would sodium be with in the second reaction? Nitrate? No, in the second one. Sulfate. Does that make sense? Okay, so sodium would then be with sulfate? Yeah, my bad. Okay, so that makes sense, right? So why would nothing form there? It's a group 1. All right, this sodium would now be with who? Would a solid form? Nope, so we're going to put an X in that box. So see if you can go through and see if you can fill out this entire thing. Some of them will be faster than others. Some of you are actually going to have to think. All right, so I'm going to go across each row. So did you guys get a solid in barium nitrate and potassium chloride? No, very good. Okay, why would barium chloride not produce a solid? What's chloride's rule? Very good. Silver, mercury, lead. All right, what about AgNO3 and KCl? Very good. AgCl. And what about nickel nitrate and potassium chloride? No. Very good. You should not have anything in there. Okay, keep going. All right, what about lead nitrate and sodium sulfate? What'd you get? Very good. PbSO4. Sulfate's rules are the heavy metal bad guys and Cabasur, or CBS, okay? All right, what about barium nitrate and sodium sulfate? Very good, BaSO4. All right, what about silver nitrate and sodium sulfate? Very good, very good. Ag2SO4. Did everybody get that 2 in there? Okay, fantastic. And then nickel nitrate and sodium sulfate. Nothing. Remember, metals and cations always go first. Okay. All right, what about sodium carbonate and sodium nitrate? No. Very good. All right, what about lead nitrate and sodium carbonate? PbCO3. Very good. Lead carbonate. All right, what about barium nitrate and sodium carbonate? Okay, what's carbonate's rule? It's soluble. Okay. Gotcha. So it is insoluble unless with group 1. Gotcha. Okay. All right, what about silver nitrate and sodium carbonate? Very good. Ag2CO3. And what about nickel nitrate and sodium carbonate? I can't see what this is. What is this? What is that? Nickel 3? All right, so Ni2CO3. Yeah, that was really bad. My bad. Okay. All right, what about sodium hydroxide and sodium nitrate? Nothing. Lead nitrate and sodium hydroxide. Very good. PbOH2. What about barium nitrate and sodium sulfate? Nothing. Very good. Those would both produce strong acids. Okay? Excuse me, strong bases. All right, what about silver nitrate and sodium hydroxide? Silver hydroxide. And then what about nickel nitrate and sodium hydroxide? Very good. So NiOH3. I think you guys get the hang of this, right? What are the ones in the bottom will not work? Matter of fact, the bottom is just like the top row, isn't it? Okay, bottom is just like the top because it's both halogens. All right, very good. So moving on. So a chemical analysis of a mixture by precipitate reactions: mix starting the chemicals to form an insoluble salt, filter out the salt, and then dry to a constant mass, and then use stoichiometry to determine any desired quantities. And again, this is everything we've done up until this point. Okay, it's just giving you the how to analyze one of those precipitate reactions. Okay. So here's a particular equation. So calculate the mass of solid NaCl that must be added to a 1 liter of a 0.1 molar AgNO3 solution to precipitate all of the silver ions to form AgCl. So here's what we're going to do. Help me read that again. So I've got a beaker, and in this beaker, how much is in there? Okay, so it's 1.5 liters, and what's the concentration? 0.1 molar. Okay, and it's silver chloride, right? Whoa, where did that come from? Silver nitrate. What am I doing? Okay, so in this beaker, we've got Ag plus and Ag plus floating around, and I've got NO3 and NO3 floating around. And what we're going to do is we're going to take a salt shaker. Okay, and this salt shaker is sodium chloride solid. Okay, when I dump that sodium chloride solid into that water, what's the first thing that's going to happen? Is it going to dissolve or is it going to sink? It's going to dissolve. Well, okay. What would happen if you start stirring it? It will dissolve. Thank you. I guess I should have asked it from that perspective. So when you pour it in there, is it going to form ions? Yes. So I'm going to have Na ions, chloride ions, and chloride ions. Now, is there anything in that particular beaker that could form a precipitate? What? Very good. So there is a chance that we can get some AgCl solid precipitate. So what we're trying to do is, if you go back and reread this question, is how much solid NaCl would there need to be added to that solution to precipitate all of the silver ions in the solution to form silver solid? Does that make sense? So in this beaker, we're trying to get all of these AgLs to turn into a what? Turn into a solid. Go ahead and ask. Does this make sense? Okay. Now, so the first thing that I want you guys to do, and I don't want you to do the bottom one. See if you can jump right into the net ionic. Because think about it. What are we trying to get as a result? AgCl. So, or do you agree that those are the only two things reacting? See if you can do it. If you need to write the full equation and then bust it in your brain and then write the net ionic, I want to get to the net ionic. If you have to write the full thing, go ahead and write the full thing. Getting hungry. No. As a matter of fact, some of you possibly got this wrong. Ah, crap. I'm going to be honest with you guys. A regular equation would have sufficed here. We'll talk about it in just a second. And there's a reason why. Because in reality, if we wanted to write the net ionic equation, here's why. Because what do we always say about solids? Leave them alone. Technically, we're trying to get back to this, right? But just kind of, I'm not going to get off on the depths of this. But if you wanted to write a net ionic, you would have done Cl minus plus Ag plus yields AgCl solid, right? That's what you would have done, but that's okay. We're not going to worry about it. So, but what we're trying to get back to is essentially the mass of solid NaCl. Now, my question to you is they give us information about the silver nitrate solution, which is right here, and they tell us that it is 1.5 liters and 0.111 molar. And they're asking us what? How many grams of that? Are these problems easier than other stoichiometric? Yes. The reason they're much easier is because you don't have to find as much of the masses. Remember, when we talked about going from grams to grams, that was a pain in the butt, right? Because you had to find 2 masses. Well, in this case, it's not as challenging because how many masses do you need? 1. So what is the only way to go from silver nitrate to sodium chloride? I got to find my mole to mole. Well, is the information that they gave us already in moles? Well, how do I get the information they gave us into moles? Multiply. Very good. So when I multiply these two numbers, what did you come out with? 0.150 moles of AgNO3. Would you agree or disagree? Does that make sense? Okay. Now, I'm going to come over here and finish the rest. Actually, I'm just going to use this and go right there. So now I'm already in moles. What's my next step? Mole to mole. So the moles of the AgNO3 to the moles of the NaCl. And then what's after mole to mole? No, sir. Okay, so that's what it would look like. So the 0.15 moles of silver nitrate, then we go mole to mole from silver nitrate to sodium chloride, and then moles of sodium chloride to grams of sodium chloride. Wouldn't it have been really nice if the problem said how many moles of sodium chloride? It would have been really nice, right? Why? You wouldn't have had to find any masses, because masses are pain in your butts. All right, what is your mole to mole ratio? 1:1. Well, that's good. And some of you actually already have the mass of sodium chloride memorized. Some of you, and that's fine. I don't expect you to memorize all of them. 22.99 plus 35.45. And then minus 0.1. That sounds right. All right. So how many grams did you guys come up with? Dustin, did you do all of it? 8.76 grams of NaCl. Don't worry about it. I don't care. Exactly. Yeah, you have to go from one thing to the next, right? Bottom line is, what was the question? Mass of solid NaCl. Do you agree that's our end result? Okay. What was the data given in? Volume and concentration of silver nitrate. So bottom line, you've got to use the volume and concentration of silver nitrate to somehow get to the mass of silver chloride. This is the only way to really get to do it. You've got to get to moles, right? And then you've got to go to mole, and then you got to go mole to gram. So really, this is really the best way to do it. Okay? All right. Look at the next one. See if you guys, let me read this before I send you off on your way. Aqueous solution of sodium sulfate and lead nitrate are mixed. PbSO4 precipitates. Calculate. Oh, boo. Yep. Boo. You gotta find the limiting reactant. Yeah. All right. Here's what I want you to do. Ignore the question. The first thing I want you to do is write a balanced net ionic. See if you can do that. Let's start there, and then we'll fill in the pieces from there. No, just the balanced net ionic. All right. So I'm going to kind of look at net ionic as backwards. Remember, if it's ever a gas, a solid, or a liquid, what do you write? Do you bust it or do you leave it alone? You leave it alone. So is there anything up here that we had to have left alone? Very good. And how do you know you had to leave it alone? It tells you it's a precipitate. And is that a product or a reactant? It's a product. So if you have PbSO4 solid. Now, that's the only thing we're going to have in our products because it's the only thing that's solid. Now, the deal is remember when you balance, bust, and then cancel, what are the things that you cancel? Things that are same on both sides, right? So when you bust them, if it's aqueous, so really over on the reactant side, do you agree those two things are going to be different because they were originally in a solution? Yes. So we would have Pb 2 plus SO4 2 minus. So that is your net ionic equation. If you know what your precipitate is, you know what your two reactants are. Do you need coefficients in this case? Yes. Okay, yeah. But are there any coefficients in this case? There are? Not in this case, no. Go ahead. Yeah. Bingo. Yep, I could put sulfate first and lead second. It does just like a normal, because if you really think about it, Justin, it's lead nitrate and sodium sulfate over here. You still don't see the other two that are hanging out. Okay. Now, so let's go to the problem. What is the question? Okay. So would you all agree that this is fair to write? That's my question. Now let's look at the data they gave us. They gave us, says when 1.25 liters and a 0.05 molar solution of PbNO32. Who does that belong to? Where does that go? The lead ion, right? It's the reactant. So we've got 1.25 liters and 0.05 molar. Does that make sense? Okay. And 2 liters of a 0.025 molar sodium sulfate. Who does that go to? Okay. Very good. So we've got 2.00 liters of a 0.025 molar. Go ahead and ask your question. It's the whole, it doesn't matter. It would be the whole thing. You wouldn't have to worry. You could really use sulfate because it's the same thing. Now, here's the deal. My question to you is, and we've done problems just like this before. In fact, they're easier than ever before because we don't have to find any masses. Which one of the two reactants do I pick to go to the other side? Don't know yet. I got to find the what? I got to find the limiting reactant. And again, the reason that this is easier is because you don't have to find any masses of compounds. What do you do with volume and concentration? Just multiply them. Very good. Now, what is 1.25 times 0.05? 0.0625 moles. Okay. Now, what is 2 times 0.025? 0.050 moles. Now you just have to identify which one is your limiting reactant. Sulfate. So this is my LR. And from this point, did it get fairly simple? Okay, it's a what to what conversion? A mole to gram conversion. Do y'all want to go through this? You pretty much got it. Do you want to do it? Okay, let's stoich it up. All right, so I've got 0.050 moles of sulfate. Here's what scares me right here. I'm just talking out loud. The reason I don't think this matters when it says R mixed is because what am I calculating? What unit? The grams. So does the grams have anything to do with the volume of a total solution? The total volume of the solution? No, I don't think it does. So I'm 99.999% positive this is still correct. Okay? All right. So now we know we're going from moles of sulfate to moles of the solid, and then from moles of the solid to grams of it. Yes, sir. Nope. You wouldn't. You would never have to do that. That's why you can do it this way, is because there is no grams involved. It's straight solution. All right, what is your mole to mole ratio between these things? 1 to 1. That's really easy because that's based off your coefficients. And again, the hardest part is if you got to find the mass, it's a pain in your butt. Okay. Thank you. 303.26, and I knew that was going to be a larger mass, simply based on the fact that lead's 207 by itself. And then there's 4 oxygens. So that's, yeah. So, and then you just multiply those two numbers. Anybody got a number? Like it. So 15.2 grams of PbSO4. Okay. So this question looked difficult from the beginning, but if you think about what you start with, you think about what you're given, and think about where you're going, it simplifies itself because you can only go one step at a time, right? Think about what the question is. Think about what they gave you. How do I get from what they gave me to where I need to go? You can't get any more complicated than that. Question first. Reaction. Yes. Yes. Let me show it to you. Yeah. First question. When it says solution, do you agree that means it's ions? Okay, so I am going to need your help here. So it says sodium sulfate. And what else? Was it lead? What? Nitrate? And then PbSO4 solid, and and then NaNO3. And this is also going to be aqueous. Okay? So remember, if it's aqueous, go ahead. So double replacement. You've got Na and NO3. Okay? So if it's aqueous, we bust it into ions, right? So it's 2 Na plus SO4 2 minus plus it's aqueous. So what do? You bust it. So Pb2 plus, it is rain, plus 2NO3 minus. Okay? Now, then we get to the other side. What do we do with it? Keep it very good because it's a solid. So PbSO4 solid. And then NaNO3 is aqueous. So what do? You bust it. Very good. So oops, sorry. Now, I know that I did not balance this properly, and I'm going to go back and do that. Okay? So I've got 2 here. I've got 2 here. So over there, I need 2 and 2, and I really should have already had a 2 right there as well. Okay? So here's the deal. The way we determine our net ionics, you cancel off what looks identical on both sides. So what looks the same but did not change at all? Sodium and sodium, nitrate and nitrate. So what you're left with is this, this, and that. So that is your net ionic. Does that help seeing it one more time just like that? Again, do you realize, now do you know why that I'm real, like I want you to get in just the ability to jump right in? Because that can take a while. It really can. Go ahead. Don't worry about all 3 of those. That's 3. That's 3. That's 3, and that's 3. So your answer is 3. I just didn't put a 0 right there. I'm really bad. No, that's only when you're adding and subtracting. Okay. Yeah. I can see what you're saying there. I'm really bad about when it does stuff like this. I leave those extra zeros off. See what I'm saying? And like right here was 0.0, like that 0. I'm really bad about leaving that off in my math, but I always end back up with a right significant figure. Even though I should do it right, I just don't, and that's a bad habit of mine. Go ahead. Yeah. Uh-huh. Yeah. 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 Yep. Okay. All right. Any other questions on that one? Go ahead. Yes, this is solid. Okay. Now, so this is where the notes picked up. Yes or no? Ish. All right. So I've covered this briefly. So let's just go ahead and hit the high points again. Remember, acid-base reactions. Remember I gave you there were 3 definitions of acid-base. One was Arrhenius, long time ago, and he said that acids were hydrogen donors and bases were hydrogen acceptors. Right? Excuse me. Check. That's wrong. He said that acids were hydrogen donors, and then he said that bases were a hydroxide. Okay? Then what did we find out was not true? All bases do not have hydroxides present. That's when Bronsted-Lowry kicked in. And instead of them being a proton donor, he called them instead of them being a hydrogen donor, he called them a proton donor. So let's read it. So an acid is a proton donor. And what's another way of saying a proton? The hydrogen ion. That produces hydronium. And again, what is hydronium? Very good. It is H2O plus H+. I may would jot that down. So it's literally like a water molecule hooked up with a hydrogen ion. That's what happens. It ain't supposed to happen. And if you want to even make it more fancy than that, you can draw this. Yep. That. It's heavy water. I mean, that's what hydronium is. Okay, what shape is that? Trigonal pyramidal bond angle. Yeah, that's right, 107. Okay. Yeah, 107. Polar, nonpolar. It is polar. Type of bond. What type of IMF? It's got some bond going on, right? It's a hydrogen bond. Okay. All right. So that's what makes an acid. A base is a proton acceptor. Now again, that is Bronsted-Lowry's definition. Arrhenius said it provides a hydroxide and a cation in water. But then again, we found or ya. That's ya. Ammonia. We found it, and Bronsted-Lowry said we've got to change it to a proton acceptor. Okay? So neutralization is when? This is a huge, huge, huge thing. Please circle that first bullet. When the moles of acid are equivalent or equal to, again, I say the word equivalent for a reason. When the moles of acid are equivalent to the moles of base, it is called the equivalence point. Okay? Do me a favor. Beside that bullet, write this right here. And I know that makes absolutely no sense, but I promise you it will come into play later. Sir? That's not true. And here's where everyone gets kind of like, I don't know what you're saying. When you think moles of acid equal moles of base, what do you assume the pH is? You assume that it's neutral. That's not always true. Okay, that is not always true, and we'll talk about why and how. And I've got a self-confession here. One of my weakest points in all of AP chemistry is acid-base. And so this is where sometimes I'm just going to have to stop and stare at it for just a second to make sure that I'm telling you correctly. Okay, the products formed are salt, which you guys should know. Are some of them soluble and insoluble? Yes, so that's where the turn is going to take from this year is we've got to figure out if that salt from an acid-base reaction is precipitate or not. And water, which we already know. Okay, now I've already begged and begged and begged to make sure that you already know these. Is everyone on the same page as this? You better be. If not, well, they're going to come back and bite you. All right, so here's what we have. We have milk of magnesia, okay, which they are calling, and if you want to write this at the top, this is MgOH2, okay, milk of magnesia. Is that weak or strong? Nope, I'm wrong. I'm an idiot. Thank you. That was stupid. You got me. All right, so this is a weak base. Now, there's a way you can tell it's a weak base. No. We're mixing it with, right here, this is HCl. It is strong. Now, what do we know the difference between strong and weak? Okay, so let's look at this particular diagram. Now, I'm going to write this word. It's called and if you want to write this underneath these pictures, it's called a particulate diagram, not piegram. Thank you. Okay, well, it was a D. I just pulled the loop up too fast, not all the way down the thing. So, this is a particulate diagram. So if you ever see or hear this phraseology, that's kind of what it's talking about. Okay, particulate diagram. How can you look into these two circles and simply know if it's strong or weak only based on the pictures alone? This tells you that those are ions. Do you see any compounds, any atoms connected together? No. So this is 100% ions, which tells me it's what? Strong. Well, they're ions. Yes. Okay, very good. But this right here, what do you notice about all that? It's together. Is it possible for some Mg2+ and 2 OH minus is floating around in there. Yes, now that's something weird. Let me ask you something. Why did I say Mg2 plus and 2 OH minuses? Very good. So for every 1 Mg that falls off, how many OHs? 2 of them fall off. Just keeping it stoichiometrically congruent. Does that make sense? Okay. What? What? This is a good one, right? Okay. So then we go through a reaction. And do me a favor. This right here is called the intermediate. That is the arrow. That is the part of the chemistry that you can't see. That is the part of the chemistry that is never discussed. It is what's going on during this reaction. So some of the hydrogen chloride is going to react, and it's going to knock some of that magnesium chloride apart. Okay? It's raining really hard. Hope it's raining at my house. So, yeah, my yard's super dry. So when we look over here on the other side, notice what we have show up. It's kind of funny. We've got the chloride ion, we've got a water molecule, and we've got a magnesium hydroxide. Based on the previous pictures, what disappeared? The hydroxide ions disappeared. Now again, were there many floating around to begin with? No, we said there were very few because it's a weak base. What else disappeared? The hydrogen ions. So think about that. You've got a hydrogen ion floating around, and you've got a hydroxide ion floating around. What can those two things form? Water. Okay, so that's how you have the hydroxide and the hydrogen forming water. Now, the other two things that are hanging out are the chloride ion and the magnesium ion. Notice what state they're in. What state are they in? The ion state. If it were a solid, would it be an ion? No, they would have clumped together and precipitated out. So there's two ways to know. Look right here. You've got aqueous and you've got liquid. Also, look at your picture. Do you see anything floating around? No, it's colorless. Okay, so that's kind of how you can tell. So you start with a very thick, milky white solution, okay, and you pour the the hydrochloric acid in there, and it turns clear. Does that make sense? Neutralization, yes, because it's an acid-base reaction. It's a weak a weak base with a strong acid. Yes, sir. We're going to do it in titration form. Wow. This has to do with hydration forces. And yep. Yep. Yeah. Say that one more time. It's a soluble compound. It's not insoluble. All right. Now, I know this is where the video picked up. I'm only going to say one thing. I don't want to write this. If it's strong, what do you write for net ionics and acids and bases? Strong all the way win. Yeah, because they made fun of me because I said it that way one time. So what is the ion for an acid? Or hydronium. You don't, and the reason, and I'm going to show you why later. Keep that in mind. Okay? If it's a base, it will always be OH minus. Why? Okay? All right. If it's weak, what do? The whole compound. Now, writing these net ionics is really going to come into a big handy later on. I'm telling you, this is the foreshadowing. Remember, this is a huge this is like a Velcro beach ball. Okay, I'm throwing this at you. Okay, so I'm telling you, this is going to come back to you at some point in time later in the year of memorizing and remembering this. If it's strong, write the ion. If it's weak, write the whole thing. Sir. Oh my gosh. That would be awesome. I would do it if you can find one. That's fine. Nobody would do it. They wouldn't understand. Okay. So let's look at this right here. So we've got strong base, strong acid, NaOH plus HCl. Here's the kicker to all of this. You can memorize strong, write the ions, weak, write the compound. But if you look at that reaction and have no clue if it's strong or weak, you're screwed. Period. You are screwed. So that's how important knowing these 14 things are. Okay? So when you come back and you look at this, you could say NOH. I already know that's strong. All right, HCl, I know that's strong. Well, that's H plus OH minus, and it always yields water. This will always 100%, 1,000,000% of the time be your net ionic reaction for strong. Always and forever. Okay? Then when you look at your strong acid, weak base, notice what happens. Look at your hydrogen. B stands for any base. Matter of fact, here it is. Here's our example. Okay? So we've got HCl plus NH3. Notice what happens. What do? You add the ion, and you just literally stick it on your base and make it a positive charge. So look at it. You have NH3, you just add the hydrogen to it, and it's NH4+. You may not have a clue what that base is, and I'm telling you, you're going to see some funky ones, just like methylamine. You've never seen methylamine before, but if you understand that it's a weak base, which it should be told to you, all you do is just stick the H on it. But here's where some of you are going to get confused. Why did they not write CH4NH2+? Okay? I'll need you to think about this. Okay? Every carbon has how many bond locations? It has 4. Okay? So I've drawn this. Well, then I'm not spending time on it. All right. So stay with me. My bad. I'm going to show you. This is? It does. So every carbon has 4 bond locations, right? Because it's got 4 valence electrons. What are 3 of the carbon's bonds taken up with? All right, so I've got hydrogen here, hydrogen here, hydrogen here. Now, currently, as it's written, we know that there's an N and 2 H's left. Which one of the 2 can have multiple bond locations remaining? The nitrogen. So we know that the nitrogen is going to take up that location right there. You with me? We almost out of time? Okay, real quick, and I'll be done with this. So we've got here and here left. But, listen, how many valence electrons is nitrogen supposed to have? Valence. 8. 2, 4, 6. What's missing? Please stay with me. Here's the deal. Watch this. So, we have this hydrogen ion floating around out there. What's the only thing in a hydrogen ion? 1 proton. We don't talk about neutrons. That's null and void. We've got 1 proton. How many electrons would it need to be happy? 2, because who does it now look like? Helium. It has none, it needs 2. Well, guess who's got 2 to give it? So what we do is we take these 2 electrons and we donate them to this hydrogen. Now, Before I did that, that entire compound was neutral or charged. It was neutral. Well, as soon as I add an H plus to it, it now becomes charged. But my original question was, why is it not written CH4NH2 plus? The hydrogen attaches to the nitrogen, not the carbon. Does that make sense?